Hello, dear students. Let us switch into the problems under design of compression members. First problem, let us see. Determine the design compressive load for a column ISHB 350 at 710 Newton per meter, 3.5 meter height. The column is restrained in direction and position at both the ends. Use Fe 410 grade steel. So that means the they have given the column is restrained in direction and position at the both ends. That means both the ends are fixed. So it will help us to find out the effective length of the column. So from the steel table, let us try to find out the property of ISHP 350 at 710 Newton per meter. Always in the steel table, instead of Newton per meter, the value will be given in terms of kgs. So whatever the value 710.2 is there, you just divide with the 9.81, you will get in terms of kgs. So your first and foremost thing whenever you get a problem is, when you get the rolled steel sections like ISHB, ISMB, ISWB, whatever it may be, you note down the properties of such a rolled section from the steel table. So from the steel table, let me search for ISHB 350 at 710.2 Newton per meter. So morning I have shared the steel table. So in the steel table, this is I section here. So you can see this is rolled steel beam for I section. This is I section. So I have to search for ISMB, sorry, ISHB 350. This is ISHB 350. The weight is given 72.4. There is another I section ISHB 350 with another weight, that is 67.4. 67.4 into 9.81 will not give us 720. So 72.4 will give us 720.2 Newton per meter as the weight. So here the sectional area you can note down 92.21 centimeter square, or 92.21 into 10 to the power 2 millimeter square, or 9221 millimeter square. Then depth of the section is 350. Then the width of the flange is 250 mm. Then thickness of the flange is 11.6 mm. Then thickness of the web is 10.1 mm. Then moment of inertia about x-x axis, or we can also consider the x-x axis as a zz axis. So izz is 19802.8. Then iyy is 2510.5 centimeter to the power 4. Similarly, the value of radius of gyration about zz axis is 14.65 centimeter, and that of ryy is 5.22 centimeter. You can convert all these in terms of millimeters only. So out of rxx or rzz and ryy, the least value is taken as the minimum radius of gyration for the calculation of slenderness ratio. Let us list out all these values. So the listed values are given here. So all the values are given. Rz is 146.5 and Ry is 52.2 millimeter. So R minimum is 52.2 millimeter. So now for steel of grade Fe410, the yield strength is 250 Newton per millimeter square, and partial safety factor for material is 1.1. The actual length is 3.5 meter. We will calculate the effective length little later. So there are two methods available. The first method is by making use of the table 8 and table 9, to be specific table 9 according to the buckling class, and another one is using few formula and without using those tables. Let us see first method by using the tables. So now from table 10, let us first fix the buckling class. The table 10 of IS 800-2007 gives us the buckling class ABCD. So to decide that table sorry to decide the buckling class, we have to refer the table which is given in page number 44. So this is table number 10. This is the I section. Rolled I section is given in the problem. So I have to judge which type of section it is. So to choose the section, first of all I have to find the ratio between h divided by bf. H means depth of the section, bf is nothing but width of the flange. If h by bf is greater than 1.2, so here we are getting 1.4, it is greater than 1.2, then the buckling axis is zz axis and the buckling class is E. If the thickness of the flange is less than 40 mm. Here the thickness of flange is 11.6 mm. That means the buckling is about YY axis and it is class B, or buckling class is B. Now here RY is less than RZ. Here you can clearly see RY is less than RZ. So the design compressive strength is governed by the slenderness ratio, and also the column will buckle about YY axis because RY is less than RZ. Therefore, now let us calculate the slenderness ratio lambda equal to KL divided by R minimum. R minimum is nothing but RY. KL, how to choose K? K is nothing but, or KL is nothing but the effective length. It is the case both ends are fixed. So for both ends are fixed, from table number 11 we have the last case, the effective length is given by 0.65. So 0.65 into L divided by R minimum works out to be 43.58. Now from table 9B, page number 41, how I decided it is table number 9B is that this will buckle about YY axis. Therefore about YY axis it is class B. So I have to choose, or I have to select the table 9B. This is table 9B to calculate the design compressive strength for given value of Fy and KL by R. So here the value of KL by R is equal to 43.58 and Fy is equal to 250. This is the Fy value, and our 43.58, that is the KL by R, is in between 40 and 50. So between 40 and 50 the values are 198 and 183. You interpolate between these two to get the value of FCD. So we get, upon interpolating, FCD equal to 201.704 Newton per millimeter square. So after this we have to get the design compressive load. Design compressive load PD equal to AE into FCD. So upon solving we get the answer as 1859.91 kilonewton. There is another method. The second method is by using some other technique, the formulas. So here for buckling class of B, which is already decided, the imperfection factor given in page number 35, table number 7. Let me go to page number 35, table number 7. The imperfection factors for B class is equal to alpha 0.34. So 0.34 is the value we got. So this alpha is required for us for the calculation of phi. So let us see how to proceed with this. So once we get the value of alpha, the non-dimensional effective slenderness ratio lambda, according to the page number 34, clause 7.1.2.1, we can calculate the lambda equal to square root of Fy into KL by R whole square divided by pi square into E. So upon substituting we get the value of lambda equal to 0.49. Let us calculate phi value is also given in the same clause, 0.5 into 1 plus alpha into lambda minus zero point 0.2 plus lambda square. So upon substituting we get the value as 0.669, the phi value. Now we will calculate FCD value, which is given. The formula is given here, FCD equal to Fy by gamma m naught divided by phi plus phi square minus lambda square to the power half. So upon substitution of the values we get 202.18 Newton per millimeter square, very near to the previous one. Therefore design compressive load PD equal to AE into FCD, the answer works out to be 1864.3 kilonewton. From the previous method we got 1859.91 kilonewton. Only a difference of about 4.5 kilonewton is there. It doesn't matter. Okay, this is how we can solve the problem. Thank you for watching. We will take up few more problems in the coming class.